then, let me just define the optimal policy. So once you have the value function, that value function is going to enable you to compare two different policies. And you're going to always take the policy which is giving you a better value, right? Because if one policy you expect playing it, you are going to win, you're going to stick to that one, right? So this is how we can define the notion of having a better policy. So let's say policy pi is said to be better than pi 2. You can show it in this form. You can say that pi 1 is more than or equal by pi 2. And you can read it, pi 1 is better than or equal by pi 2. Okay? And what does that mean? It means that if you go ahead and compute the value function for pi 1, this is going to be more than the value function for pi 2. Okay? At every single state. Very important, right? You pay attention to that. This value function is a function of state, right? So this means that when you play policy pi 1, you should always get better value regardless of what state you are in. If one policy is giving you a good value in one state, but when you change your state, you're going to end up with worse value, then this is not better value than the other one, right? If one policy gonna win you when you start at one cell, but it's gonna make you lose if you start at another cell, there is no reason that this guy is better than another policy which wins you in the second cell, but it makes you lose in the first cell, right? So it doesn't matter, right? If you have one policy which is always winning you or making you draw at any cell starting, right? And one policy that loses you in one particular case, then in that case you're going to say that policy is better, right? So this is very important. This should be for all possible states, this condition. Everybody's clear? Yes?
What if, for example, you have like 10 states, what about like 8 times you will win, only 2 times you will lose?
Yeah, but the question is in that two possible cases. Say you have 10 states, right? And in 8 states you win, in 2 states you lose when you use policy pi 1, right? Then with policy pi 2, if you say that pi 1 is better than pi 2, you should definitely lose by pi 2 in those 2 states, right? And maybe there are more states that you lose, right? But if you win in at least one of them, or draw in at least one of them, then you cannot say pi 1 is better than pi 2, right? Because in that particular state, if you play with pi 1, you're going to lose. But if you play with pi 2, you're not going to lose. So there's no reason that this policy is better, right? Questions? Okay, so if you got no question, this is going to help us define what we call it the optimal policy. So what is the optimal policy? Well, the policy which is better than any policy is the optimal policy, right? So the policy which is going to end you with the best value, best result you can think of, regardless of what state you are at. Okay? So, as I told you, this is again this is the point that I just tried to indicate in the previous slide. So it should happen for every single state. And then if you have one policy which is better than any other policy, then we call it the optimal policy, right? So policy pi star is called to be the optimal policy. If any policy that you suggest instead of pi star, when you just compare their value function, pi star is going to give you higher value for all the states, right? Then this is the optimal policy. Everybody's clear? Question? No question? So what is the whole purpose in reinforcement learning? To find pi star, right? You want to know what is the best policy, right? That's the whole story, right? What is the best policy? Because this is going to give me the best expected reward that I expect to collect all over the game. That's the best thing to do, right? So the whole problem is to find pi star for a given environment, right? So somebody gives you an environment, you have some access to state and the transition and the rewarding system of that environment, and now you want to find out what is the best policy that you can play, right? Okay, so now people might define it in this alternative form. This is eventually the same thing. Just to see the notation, you might say that the policy, the optimal policy is the policy which is going to maximize the value function. But the key point here is that this value function is not defined in one single state. It's defined on all the states, right? So this value function, you can think of it as a table, right? Table of value, and this is for state 1, state 2, state 3, so on, right? Okay. Now, one question that you might ask is that, is there the optimal policy for any environment? Well, if we think that the environment has a well transition, not that we know it, but that exists. The transition function exists, the rewarding system is consistent. If such a thing exists, then you could say, yes, there is optimal policy. But whether we can access it or not, well, this is not the question, right? So that is a hard question to answer. The whole RL literature is about that. But does it exist? Yes, that exists. And the other point is that why we define it using the value, why we think only about the state. Didn't we also define the action value? Like we say that if we are in one particular state and we do one particular action, what's going to be the collected reward, right? That is the action value, the Q function, right? Well, you can define it as well. It's going to be equivalent to this one. So I define it in this way. I told you that when you have the optimal value function, this means that you play with the optimal policy, then this value function is going to be the function which is the maximum, giving you the maximum value among all possible policies, right? You can write the same way for the Q function, right? So if you know the optimal policy, then the Q function that you're going to get out of that optimal policy is going to be, again, the maximum Q function. Like if you play with any other policy, you're going to get a smaller action value, right? Now, it might be a bit surprising right now, but once you do assignment 1, you're going to see it immediately, right? Because the only difference action value has to value is that you are not averaging the first action, you're averaging anything else, right? And then as long as everything after that is optimal, this is the only things that depend on your policy, right? Then your action value is optimal as well. But no worries, as I told you, we're going to play a lot with this stuff. This is only just to define it for you. We're going to play a lot with this stuff and going to get very clear. Questions? Yeah. It exists. Yes, you can find it, right, right. If you know that this environment can be described, right? So for example, in the trading environment, I cannot really say what is the state and how is the transition, right? So I cannot even think about this, right? Yeah, it's a very hard thing, right? But if you can think about that, if you can model that, if that is there is a consistent way of defining the environment, it's not going to change totally. Like you cannot play optimal with me if I am a totally illogical person, right? So if I just want to offend you, right? You say, I play this, okay, you are going to get bad reward. Why? No reason. Yeah? This person is just changing decision, right? The environment is changing, right? That thing you cannot play optimal, right? But if the environment has a consistent rule, right? Even if that's random, but this is randomly happening, right? It's always consistent. You don't change. Like I have a bunch of rules in my mind. Maybe those rules have random component in them as well, but I have them in my mind, and then I keep playing with you in that way. Then there is definitely one optimal policy to play that. This could be as dummy as playing random, because the environment is totally random, right? But there is one way that is the best way of playing it.
Just a follow-up question. So you mentioned that there are two components in this course. One is the traditional RL, the other is like deep RL.
Yes.
So basically in traditional RL, we are targeting those problems where we can find the optimal policy, but in
No, hopefully I'm going to break it shortly today, but the main idea is that like in both cases you are doing the same thing. So you can formulate the optimal policy. The issue is that you need to know the environment to be able to determine it. And then in practice you don't know the environment, you don't know those rules. So the thing is that you start to estimate it, right? When the problem is small in dimension, you can do the estimate simply by building a table, right? This is tabular RL. But if the problem is huge in dimension, then you cannot do it. Then you use deep learning. So you would put one network to approximate this value and action value functions for you. And then you use that approximated function to again find the optimal policy. By the end of the day, you're solving the same problem with different computational tools. Right? Questions? No question? Okay, so if you got no question, one important notice here, there is no reason that your optimal policy is unique, right? It might be that playing one game, you have multiple policies that end you up with the same result, right? But they are all ending you up with the same value, right? So it's not like a better optimal policy. All optimal policies are giving you the best value, and all the values are exactly the same, right? But there's no reason that there is one policy. It could be multiple policies. Okay. So yeah. So the ultimate goal in the reinforcement learning, as I told you, is to just find the optimal policy. And then how we can do this? There are a bunch of challenges here. The first thing, so as I explained it briefly right now, so when you know the environment, if you have a consistent environment, it means that the environment is not changing its nature by any reason. So it's not like the Earth physical rules, and immediately out of sudden it's going to become Mars, and then immediately become Mercury, and not such a thing, right? You are playing on Earth with the physical rules of Earth, right? Then this means there is a consistency in this environment. It's not going to change unnoticeably the behavior, right? And in that case, the optimal policy exists. Yeah? And the whole question is how I can find it. Now, to find it, I need to have a model of the environment, right? Either I do need to know the dynamics of the environment, or I should be able to describe that behavior of the environment by some random process, right? So the first one is quite hard in practice. Some people do it on basic control systems. They used to do it. But typically, we just describe it by some stochastic model, right? Like we say, we play a component with some chance do this, with some chance do that, right? So if I have the model, then I need to have the model. If I have the model, then I can just formulate whatever we did today, all towards, like, I can efficiently formulate everything, and I can efficiently find out what is the optimal policy, right? This is what we call it model-based reinforcement learning. This means that I do know, or I can describe how does the environment behave, and because of that I can find out what is the optimal policy, okay? But the other case is that maybe I don't know. I do know the level of stochasticity, the level of randomness inside. I cannot describe it, right? Then what I can do? Well, this is where the statistical techniques come into account. So we can just try to use a statistical technique, things like Monte Carlo approach, temporal difference, approaches like that, in order to get an estimate of what we need. For instance, say I want to just find out what is the action value at one particular state S when the action A has been done, right? Well, if I know the statistical behavior of the system, I can describe the next state and so on, right? But if I don't know that distribution, what can I do? Well, I can get to that state exactly play action for 1,000 times, right? And I let it go forever, right? And then I see what is the reward that I get. I average all of those rewards. This is supposedly, yes, this is supposedly the expected value of the return you're going to get, right? So you can average it by some statistical approaches like Monte Carlo, right? This is what we call it model-free reinforcement learning. We don't have any model of the environment. We don't know how does it change from one state to another, and we think this is random with some distribution which we do not have access to, but then we use approach like statistical techniques to compute whatever expectation we need to calculate, right? So these are the two main classes of reinforcement learning, and this does not matter whether you are doing classical tabular reinforcement learning or you are doing deep reinforcement learning. You always are doing one of them. If you have the model, you're the king. You can do whatever you want, right? You have the perfect solution. In that case, you can describe the conditions on the optimal policy, which is the Bellman equation. And out of that, you can end up with the policy or value iteration algorithm. But in the case that you don't have a model, now you only can use the statistical approaches to compute whatever you want. And then there are two different techniques there. You can either play on policy, like you just consider one policy, you play with it, you get the behavior out of the environment, then you change your policy again, you play with it, you get the behavior from the environment, and so on. Or you might go for off-policy methods. It means that I play with one policy, but at the same time, I get an estimate of the other policies as well. Can I do that? Yes, we can do it. This is the important sampling idea. Like if I know this policy and I know that how does the other policy behave as compared to my policy, then I can get a rough idea about how I'm going to end up with when I play the other policy, right? This is what we call it off policy. And then here, for example, here, as I told you, you end up with a value and policy iteration. This is the best you can do. If you are here, then you need to do more statistical approaches. Like you need to use Monte Carlo approach, you need to use temporal difference, things like this. We're going to get into all of them in this course. And then you end up with algorithms like SARSO or maybe Q-learning in the off-policy case, where you can somehow approximately find the optimal policy. Everybody's clear? Questions? So, main objective, find the optimal policy. If you know the environment, you're in the model-based. If you don't know the environment, you're in the model-free. Okay? Great. Now, one next thing is that, well, maybe I go for I don't know, model-based or model-free, any of them, and I start doing whatever I told you in the previous slide. Now, the point is that we're going at the end of the day work with value function, for example, right? And this value function depends on this state, right? Now, if I have 10 possible states, 100, 1000, well, this is one finite table, right? So I can say this is the first value, second value, till value 1000. And then I can use one technique to approximate it or evaluate it exactly, right? But what if the number of states that I have is crazy large? Is there any example like that? Chess, right? The number of cases is 10 to power 40 something, or even more even. I mean, there are papers on that to approximate the number of possible ways you can play chess, right? And none of them is finite to or computation power, right? So if you just do, I'm going to do that in the second part, but you can see that if you just do every single case, if you investigate every single case of playing chess in less than a picosecond, then if, I don't know, 10 to power 100 times, you have a time 10 to power 100 times more than the time starting from Big Bang. You're not going to end up investigating all the cases, okay? Just to give you the idea how big that could be. Then the question is that how many entries that table going to have, right? You can never end up estimating all of them, right? Or evaluating all of them, right? So that is the problem. What if you have insane large number of states, right? How you can then solve this problem? This is where the deep learning come in, right? So what we do in deep learning, we would say that, okay, in deep learning or machine learning in general, we have a function which we don't know, but we have a few points of it, right? This is our data set. Then we get that data set, we just fit it into a model. Like we get a neural network, we try to make the neural network to give us exactly the value of those points, right? And then we say, okay, if we have done fine, if we have not got too much overfitting and things like that, when you give me a new sample, this neural network is going to predict the output of the function properly, right? This is exactly what we are going to do. So we're going to say, okay, I cannot compute the value function on every single state because the number of states is insane, but I need this value function that whenever I see a state, I put it inside this guy and it gives me the value, right? So what I can do, maybe I can train a neural network on a bunch of possible states. I just candidate a few states, I compute their value, then I give it as a sample to my neural network. I train my neural network. Now, when I have a new state, I just say, okay, just let's use that value network to give me an approximate of the value. Is it exact? No, but what can I do, right? So this is where the deep reinforcement learning gets started. So you might say that, okay, this one is very simple extension of that one. Yeah, initially you think like that. But as we go inside, you see that the idea of building that neural network and training it is more complicated as you can think. And this is why all of those approaches, like the policy networks, value networks, are going to come in. And then we're going to have the actor-critic approaches, which we have both the networks interacting with each other and things like that. So the point that I wanted to make here is that the model-free and model-based reinforcement learning are